Look up on a clear, dark night, far from the glow of the city. You see a breathtaking canvas of stars, a scattering of diamonds against an infinite black velvet. It feels complete, a perfect picture of the cosmos. But what if I told you that this magnificent view, this entire starry spectacle, is only the tiniest fraction of what's actually out there? That our eyes are blind to a far more expansive and mysterious reality woven into the fabric of space itself. We are surrounded by a light we cannot see, a hidden energy that holds secrets to the birth of galaxies, the death of stars, and the very structure of the universe. This is the cosmic ultraviolet background, a faint, all-pervading glow that is one of the most significant, yet least understood, phenomena in all of modern astronomy. For decades, since we first developed the tools to peer into the ultraviolet spectrum, scientists have known this background light was there. It's not coming from any one star or galaxy. Instead, it's a diffuse, ghostly tapestry that fills the entire sky, a cosmic hum left over from eons of violent celestial events. Imagine trying to hear a single, quiet conversation in a stadium roaring with cheers. That's the challenge astrophysicists face. They must carefully subtract the brilliant light of known objects, the foreground of our universe, to listen to this faint, universal whisper. And within that whisper, they have uncovered not just one or two curiosities, but 25 distinct, profound mysteries. Each one is a puzzle piece that doesn't quite fit, a question that challenges the very foundations of what we think we know about how the universe works. This isn't just an academic exercise, it's a journey to the frontier of human knowledge. The answers hidden within the cosmic ultraviolet background could rewrite our textbooks on everything from the first stars that ever shone to the nature of the dark matter that invisibly binds the cosmos together. In this video, we are going to embark on that journey together. We will unravel these 25 enigmas, exploring why this invisible light is so baffling, what it might be trying to tell us, and how solving its mysteries could fundamentally change our place in the universe. So, let's pull back the curtain on the night sky you thought you knew and step into the brilliant, invisible darkness. So, we begin with the most fundamental of these 25 mysteries, the one that started it all. Where does this pervasive, invisible light actually originate? The story of its discovery takes us back to the early days of space exploration, a time when we were first able to lift telescopes above Earth's atmosphere, which acts like a pair of sunglasses blocking most ultraviolet light from reaching the ground. When those pioneering instruments, like the orbiting astronomical observatory in the late 1960s, pointed into what should have been the darkest, emptiest patches of space between the galaxies, they detected something astonishing. It wasn't black, it was filled with a faint, uniform ultraviolet glow. This was the cosmic ultraviolet background, and its very existence posed an immediate and profound challenge. Scientists initially had what seemed like a straightforward hypothesis. Perhaps this glow is simply the combined light of countless distant, faint galaxies that our telescopes are not quite powerful enough to resolve individually. Think of it like looking at a city from a great distance at night. From far away, you see a general haze of light, but as you move closer, that haze resolves into the distinct street lamps, windows, and headlights of individual sources. Astronomers assumed that with more powerful telescopes, like the Hubble Space Telescope, they would be able to see each contributing galaxy, and the diffuse background would simply vanish, explained away as the sum of its parts. But the universe loves a good surprise. When Hubble and other advanced observatories stared deeply into the void, they did find myriad faint galaxies. They subtracted all their light, a monumental task in itself, and yet a significant portion of the glow remained. A stubborn, unresolved signal persisted. This is the heart of the first mystery. There is light that cannot be accounted for by any known population of stars or galaxies. So, if it's not coming from the galaxies we can see, where is it coming from? This is where the debate truly ignites, splitting into two compelling and potentially complementary camps. On one side, you have the more conventional, though still extraordinary, primordial explanation. This theory points to the first generations of stars, known as population 3 stars. These would have been behemoths, hundreds of times more massive than our Sun, burning ferociously hot and bright with primarily ultraviolet light. They lived fast and died young in spectacular supernova, flooding the early universe with UV radiation. The idea is that the faint echo of that initial blaze of starlight, stretched and diluted by the expansion of the universe over billions of years, might be what we're detecting today as the background glow. It would be a fossil record of creation itself, a snapshot of the universe's first dawn. On the other side lie more exotic possibilities that push the boundaries of physics. Could the glow be a signature of dark matter, the invisible substance that makes up most of the universe's mass? Some theories suggest that when certain types of hypothetical dark matter particles collide and annihilate, they could produce ultraviolet photons. If this is true, then the cosmic ultraviolet background is not just a fossil. It's a live map of the distribution of the universe's most mysterious component. Other exotic ideas involve vast, tenuous clouds of hydrogen gas falling into the gravitational wells of dark matter halos, heating up and glowing in the UV as they do so, or even the radiation from immense, previously unnoticed streams of gas stretching between galaxies. The debate between these primordial and exotic origins is far from settled. It sets the stage perfectly for the complexity of the entire cosmic ultraviolet background. It shows us that even the most basic question, where does the light come from, leads us directly to the frontiers of cosmology, forcing us to consider the very first stars or the hidden nature of dark matter. This unresolved puzzle is a testament to the fact that we are still learning to see the universe, and what we cannot see with our eyes alone holds the keys to its greatest secrets. This brings us directly to our second mystery, one that asks us to consider not the first stars, but the colossal structures that should have formed in their wake. Theorists building models of the early universe predicted the existence of vast, glowing clouds, each one a cosmic factory for building galaxies. These are the Lyman-alpha blobs, and their apparent absence from the cosmic ultraviolet background is a puzzle that has forced a major rethinking of how the universe assembles itself. To understand why they are so important and why their seeming disappearance is so baffling, we need to understand what they are supposed to be. Picture a nebula, but on an almost unimaginable scale. A Lyman-alpha blob is not a cloud of gas where a few stars are being born. It's a sprawling reservoir of pristine hydrogen gas, hundreds of thousands of light years across. That's larger than our entire Milky Way galaxy. These immense structures are illuminated by a very specific kind of light. As hydrogen gas is energized whether by the intense radiation from newly formed stars within it, or by the shockwaves of galactic collisions, or simply by the gravitational energy of gas falling into a dark matter halo, it glows with a very distinct ultraviolet wavelength known as Lyman-alpha emission. It's like a giant cosmic neon sign, broadcasting the presence of a massive concentration of the universe's fundamental building block. For a long time, cosmological simulations pointed to these blobs as being a dominant feature of the adolescent universe. The models suggested that webs of dark matter should have funneled enormous amounts of gas into these dense knots. As the first galaxies began to coalesce within them, their furious bursts of star formation, along with the energetic processes of growing supermassive black holes, should have caused these vast hydrogen clouds to shine brilliantly in ultraviolet light. The logical conclusion was that the diffuse glow of the cosmic ultraviolet background would be, in large part, the combined light of countless unresolved Lyman-alpha blobs, their individual signatures blurred together into a cosmic haze by distance and time. Yet, when astronomers went looking for this predicted contribution, they came up short. While we have found a few of these spectacular blobs, their numbers are far, far lower than the theories anticipated. It's as if you predicted a sky filled with 100 large, bright clouds, but when you looked up, you only saw 2 or 3. The vast majority of the signal that should be there simply isn't. So, where did all the blobs go? This discrepancy has led scientists down several fascinating paths to explain the missing light. One compelling possibility is that the blobs are there, but they've been cloaked. The early universe was not a perfectly clean environment. It was filled with dust. This dust, composed of tiny grains of carbon and silicate, is exceptionally effective at absorbing ultraviolet light. It's possible that the interiors of these giant gas clouds are so thick with dust that the Lyman-alpha radiation, generated deep within, is almost completely blocked before it can escape into intergalactic space. The neon sign is there, but it's been covered in a thick layer of cosmic soot. Its light converted to heat and re-radiated at much longer infrared wavelengths, invisible to our ultraviolet detectors. Our models may have correctly predicted the formation of these structures, but they may have drastically underestimated how quickly they became polluted with the heavy elements forged in the first generations of stars. Another explanation strikes at the heart of our understanding of galaxy formation itself. Perhaps the models are wrong about the very process that lights these blobs up. The simulations assume a very efficient and rapid conversion of gas into stars. But what if star formation in these early environments is a much more hesitant stop-and-start affair? What if the gas is too turbulent or the feedback from newborn stars is so violent that it blows the surrounding gas away, temporarily shutting down further star birth before a major glow can be established? In this scenario, the blobs might exist as dark, quiescent reservoirs of gas for much longer than we thought, only flaring up briefly in UV light before settling back into darkness. Their contribution to the background would then be intermittent and faint rather than a steady, dominant hum. A third, more radical idea suggests our search might be looking in the wrong place or for the wrong thing. The light from the most distant blobs is stretched so severely by the expansion of the universe that it may have been redshifted completely out of the ultraviolet part of the spectrum and into the visible or even infrared range. Alternatively, the blobs we are trying to find might be so diffuse, their surface brightness so low, that they simply blend into the noise of the background, impossible to distinguish with our current technology. They are not missing, they are hiding in plain sight, camouflaged by the very faintness of the signal we are trying to measure. The mystery of the missing Lyman-alpha blobs is a beautiful example of how a single anomaly can force a cascade of new questions. It challenges our assumptions about the efficiency of star formation, the cleanliness of the early universe, and the very timeline of how giant galaxies come to be. It shows us that our cosmic maps are still incomplete, and that the darkness between the points of light holds structures and secrets we are only beginning to comprehend. This unresolved question about the missing cosmic structures leads us to an even more profound possibility, one that reaches into the deepest shadows of the universe. What if the light we cannot fully account for isn't coming from stars or gas at all, but from the invisible fabric of the cosmos itself? This brings us to our third mystery, a hypothesis that is as thrilling as it is revolutionary: the role of dark matter decay. For decades, we've known that dark matter exists because of its gravitational pull, a ghostly presence that guides the motions of galaxies and bends the path of light. But its fundamental nature has remained one of the greatest unsolved problems in physics. The cosmic ultraviolet background might just be our first glimpse of its true identity. The idea is tantalizingly simple in concept. What if dark matter is not entirely stable? What if, over astronomical timescales, these mysterious particles can transform or decay into something else? According to Einstein's famous equation, energy and mass are two sides of the same coin. If a dark matter particle were to decay, even very slowly, a portion of its mass would be converted into energy, potentially emerging as photons of light. And for certain theoretical types of dark matter, that light would be in the ultraviolet part of the spectrum. In this scenario, the faint, all-pervading UV glow isn't a fossil from the first stars. It's the steady, silent hum of the universe's dominant but invisible component very slowly revealing itself. It would be like hearing the faint radioactive decay of a material you couldn't see, confirming its presence and properties by the energy it releases. Scientists have proposed specific candidates for this decaying dark matter. One of the most discussed is a hypothetical particle known as a sterile neutrino. Unlike the regular neutrinos that stream from the sun and are famously hard to detect, sterile neutrinos would be even more elusive, interacting with ordinary matter only through gravity. But certain models suggest that these sterile neutrinos could be unstable. They might occasionally decay into an ordinary, detectable neutrino and a photon. The energy of that photon would be like a fingerprint, a specific wavelength directly tied to the mass of the original sterile neutrino particle. If that mass is in the right range, the photon would be an ultraviolet photon. The entire cosmic ultraviolet background could, in principle, be studied with this specific signature, a uniform background of light created by the decay of dark matter particles everywhere in the universe. Detecting such a signature would be a monumental breakthrough, arguably one of the most significant in the history of science. It would do more than just explain a puzzling astronomical observation. It would crack open the door to a whole new realm of physics. For the first time, we would move from inferring dark matter's existence through its gravity to directly understanding its particle properties. We would know its mass and have concrete evidence for its behavior beyond mere gravitational pull. This would validate theories that go beyond the standard model of particle physics, providing a crucial clue to how all the fundamental forces and particles of the universe fit together. It would transform dark matter from a cosmic placeholder into a known entity, with profound implications for our understanding of everything from the Big Bang to the ultimate fate of the cosmos. Of course, the challenge is immense. Picking out this specific decay signal from the UV background is like trying to identify a single, quiet instrument in a symphony orchestra playing from the other side of the world. Astronomers have to meticulously model and subtract every other possible source of ultraviolet light, the integrated light from galaxies, the radiation from hot gas, the possible remnants of population 3 stars, to see if a faint, leftover signal with the precise characteristics of dark matter decay remains. It's a painstaking process of elimination that is ongoing, with some intriguing hints but no definitive proof yet. The mystery of the cosmic ultraviolet background, therefore, sits at a thrilling crossroads. It could be the key that unlocks the secret of dark matter, forever changing our relationship with the hidden majority of the universe. But if the grand structures like Lyman-alpha blobs are missing, and the exotic signature of dark matter remains elusive, perhaps the answer to the ultraviolet glow lies not in the colossal, but in the countless. This leads us to our fourth mystery, a problem of sheer numbers and technological limitations, the potential contribution of a universe teeming with faint, undetected galaxies. It's a compelling back-to-basics idea. What if the reason we can't fully account for the background light is simply that our most powerful telescopes are still not powerful enough to see the smallest and most numerous stars in the cosmic forest? Imagine you're using a net to catch fish in the ocean. Your net has holes of a certain size, so you catch all the large fish and many of the medium-sized ones. But the vast, swirling population of tiny fish slips right through. You might look at your catch and think you have a good sample of the ocean's life, but in reality, you're missing the most abundant creatures of all. This is the precise challenge facing astronomers with the Hubble Space Telescope and even its successor, the James Webb Space Telescope. These instruments are magnificent, but they have a fundamental limit, a detection threshold. They can only see galaxies that are bright enough and large enough to register above the inherent noise of the universe. There is every reason to believe that below this threshold exists a truly immense population of dwarf galaxies, or even smaller star-forming clumps that formed in the early universe. Theoretical models of galaxy formation strongly support this idea. They predict that the early cosmos was a chaotic place where dark matter condensed into halos of all sizes. While a few large halos grew into the majestic spiral and elliptical galaxies we see today, the vast majority were small, giving birth to correspondingly small, faint galaxies. These tiny galaxies would have been factories for ultraviolet light, filled with hot, young, massive stars. Individually, each one would be incredibly dim. But collectively, their combined output could be staggering. If there are enough of them, their unresolved light could easily add up to the missing component of the cosmic ultraviolet background. This is the faint galaxies problem in a nutshell. We have a strong theoretical suspicion that these galaxies must exist in enormous numbers, but confirming their presence and measuring their total light is a monumental technological hurdle. The difficulty lies in the nature of the light itself. As we look back in time, the expansion of the universe stretches the wavelength of light in a process called redshift. The ultraviolet light emitted by these early, faint galaxies is stretched into the visible and even infrared parts of the spectrum by the time it reaches us. Detecting this extremely faint, redshifted light requires not just sensitivity, but also incredible resolution. We need to be able to distinguish a faint, smudge-like galaxy from random fluctuations in the background. The Hubble Space Telescope's deep field and ultra-deep field images were revolutionary because they pushed this boundary, revealing thousands of previously unseen galaxies in a patch of sky the size of a grain of sand held at arm's length. But each improvement in technology has revealed more faint galaxies without completely eliminating the unresolved background glow, suggesting the population extends even fainter than we can currently probe. This is where the James Webb Space Telescope enters the story, not as a mere successor, but as a game-changer specifically designed for this hunt. Webb's primary mirror is far larger than Hubble's, collecting more light and allowing it to see fainter objects. More importantly, it is optimized for infrared astronomy, which is exactly where the light from the most distant and faintest galaxies is redshifted. Webb is in effect weaving a net with much smaller holes. Every new deep field image it releases pushes the frontier of observation a little further, revealing galaxies that were once completely invisible. The critical question astronomers are now trying to answer is, as we peer deeper and fainter, does the unresolved portion of the ultraviolet background finally disappear? Does the diffuse haze resolve into countless individual points of light? The answer is not yet clear. Early results from Webb are both thrilling and perplexing. The telescope is indeed finding vast numbers of faint early galaxies, some even earlier and smaller than expected. This seems to support the faint galaxies hypothesis. However, there are also surprises. Some of these early galaxies appear to be brighter and more evolved than models predicted, which complicates the simple picture. The hunt is now a race against noise and statistics. Astronomers are engaged in a painstaking process of counting these faint galaxies, measuring their total light, and subtracting it from the background signal. If a significant glow remains even after accounting for Webb's newfound treasures, it would point to something else entirely, perhaps a component that is so diffuse or so uniformly distributed that it can never be resolved into individual objects, pushing the mystery into an even more profound realm. But even if we could build a telescope powerful enough to see every single star and galaxy in the cosmos, there would still be a fundamental complication standing between us and the true origins of the ultraviolet background. The universe is not a perfect vacuum. The vast expanses between galaxies are filled with an incredibly diffuse but crucially important substance known as the intergalactic medium, or IGM. This is not a uniform, empty void. It is a complex web of mostly hydrogen gas, and it plays a dramatic role in our story, not as a source of light, but as a cosmic filter that obscures and reshapes the light traveling through it. To understand the fifth mystery, we must appreciate how this interstellar fog complicates our search for the source of the glow. Think of it like trying to observe a distant city through a thick, patchy fog. The city's lights are on, and they are bright, but the fog doesn't just dim them uniformly. Some patches are thicker, completely blotting out certain lights, while other patches are thinner, allowing a murky view. The fog scatters and absorbs the light, creating a hazy veil that makes it incredibly difficult to judge the true brightness, color, and even the number of lights in the city. The intergalactic medium acts in a very similar way for ultraviolet light, particularly for the high-energy photons that make up the cosmic ultraviolet background. As this light journeys across billions of light years to reach our telescopes, it doesn't travel unimpeded. It must pass through this all-pervading fog of neutral hydrogen gas. This is where a fascinating astronomical phenomenon comes into play, one that provides both a powerful tool for cosmologists and a major complication for our mystery. It's called the Lyman-alpha forest. The name itself hints at its complex nature. When the light from a distant quasar or galaxy travels through the universe, the specific wavelength of light associated with hydrogen's Lyman-alpha transition is preferentially absorbed by clouds of neutral hydrogen gas it encounters along the way. But because the universe is expanding, each cloud is moving away from us at a slightly different speed. This motion stretches the light, meaning each cloud absorbs light at a slightly different wavelength from our perspective. The result, when we spread the quasar's light into a spectrum, is breathtaking. Instead of a single, clean absorption line, we see a veritable forest of hundreds, even thousands, of individual absorption lines, each one corresponding to a different cloud of hydrogen gas at a different distance along the line of sight. This Lyman-alpha forest is a direct record of the large-scale structure of the universe, a map of the cosmic web written in light and shadow. It tells us that the IGM is not smooth. It is a labyrinth of filaments and knots with vast empty voids in between. For scientists trying to trace the origins of the cosmic ultraviolet background, this forest presents an immense challenge. The background light we detect is not a pure signal sent directly from its source. It is the filtered remnant. Each photon has had to run a gauntlet through this labyrinthine forest. Some photons are absorbed completely, others are scattered, their paths altered. The light that finally arrives at our detectors has been processed by the entire history of its journey. We are not seeing the original source as it was. We are seeing it through the lens of everything that lay between it and us. This makes it extraordinarily difficult to work backwards and determine the exact properties of the original emitters. Was the source intrinsically faint but relatively unobscured? Or was it incredibly bright, but its light heavily filtered by a dense knot of gas in the IGM? Disentangling these two effects is a monumental task in cosmic forensics. The filtering is also selective. It doesn't affect all ultraviolet light equally. The IGM is much more effective at absorbing higher energy UV photons. This means the cosmic ultraviolet background we measure today is biased toward the lower energy end of the UV spectrum. The higher energy photons from the most distant and ancient sources have been systematically removed from the signal during their long journey. It's as if the fog selectively filters out the blue light from our metaphorical city, leaving only the redder hues, giving us a distorted impression of the city's true color palette. This makes it challenging to determine the true nature of the sources, whether they were exceptionally hot, massive stars, or something else entirely, because their original spectral signature has been irrevocably altered. So, the mystery of the intergalactic medium's filtering effect adds a profound layer of uncertainty to our investigation. It suggests that even with perfect telescopes, the universe itself has woven a veil across its deepest secrets. The diffuse glow we measure is not just a puzzle of missing sources, it is a puzzle of a scrambled signal. To decode it, we must not only find what's emitting the light, but also create a perfect model of the cosmic fog that has shaped it over billions of years. It is a reminder that in astronomy, seeing is not always straightforward believing. We must learn to read the shadows cast by the invisible structures of the cosmos to understand the light. This brings us to a quality of the cosmic ultraviolet background that is, in its own way, just as baffling as its source, its remarkable uniformity. When you look at the night sky, you see a very uneven distribution of matter. Galaxies cluster together in vast walls and filaments, separated by enormous, almost empty voids billions of light years across. You would naturally expect the ultraviolet background to mirror this cosmic geography. The glow should be brighter where galaxies are densely packed, like the well-lit downtown of a metropolis, and much fainter in the desolate voids, the cosmic countryside. But that is not what we see. Instead, the background is incredibly smooth. No matter which direction you point your telescope, the intensity of this faint UV glow is essentially the same. It's as if you were looking at a photograph of a city at night, but instead of seeing bright centers and dark suburbs, the entire image was washed in the exact same shade of dim, pervasive light. This unexpected smoothness is our sixth mystery, and it forces us to reconsider how light travels and how matter is distributed on the very largest scales. This uniformity presents a serious challenge to many of the explanations we've discussed so far. If the glow were primarily the combined light of unresolved faint galaxies, its smoothness would imply that these galaxies are distributed with an almost perfect evenness throughout the universe. But our observations of the large-scale structure directly contradict that. Galaxies are not evenly spread, they are clumped. Even the population of ultra-faint dwarf galaxies should, in theory, trace the same cosmic web as their larger cousins, congregating in the same dense regions. For the background to be so smooth, something must be acting to erase the fingerprints of this clumpy distribution, to smooth out the wrinkles in the cosmic tapestry. One compelling possibility involves the incredible journey of the light itself. The ultraviolet photons that make up this background have been traveling for billions of years. Over such vast distances, the expansion of space itself might act as a great cosmic blender. Imagine tossing a handful of glitter into a swimming pool. At first, the glitter is concentrated in one spot, but as you slowly stir the water for a very long time, the glitter particles spread out, eventually creating a uniform, sparkly suspension throughout the entire pool. In a similar way, the expansion of the universe over eons could have stirred and scattered the paths of these photons, effectively blurring out any sharp contrasts that existed when the light was first emitted. The light from overdense regions gets diluted as it spreads into the underdense voids, and the light from the voids is so faint that it doesn't create a noticeable dip. The result, after a long enough time, is a uniform glow. Another fascinating idea points back to the intergalactic medium, the cosmic fog we discussed earlier. But this time, instead of just filtering the light, the IGM might be actively contributing to the smoothing effect. If the source of the background is not just galaxies, but also includes a significant component from the warm gas within the cosmic web itself, gas that is heated by the background radiation of galaxies or by shock waves, then the distribution of that glow could be much smoother. While galaxies are highly clumped, the filaments of gas in the cosmic web are far more extended and diffuse. Their emission would naturally fill the voids more evenly than starlight from individual galaxies ever could. In this scenario, the smooth background isn't a puzzle to be solved. It's a direct prediction, a signature that we are detecting the faint glow of the universe's underlying gaseous architecture. However, the most profound implication of this smoothness touches upon one of cosmology's fundamental principles, the cosmological principle. This principle states that on the largest scales, the universe is homogeneous and isotropic. meaning it looks roughly the same in every direction and from every location. The startling uniformity of the cosmic microwave background radiation, the remnant heat from the Big Bang, is the strongest evidence for this principle. The smoothness of the cosmic ultraviolet background, which comes from a much more recent epoch, acts as a later life checkup on this principle. It suggests that even after billions of years of structure formation, the universe retains a deep-level uniformity. The clumps of galaxies we see are like froth on the surface of an ocean. Beneath them, the distribution of matter and energy, when averaged over sufficiently large volumes, remains remarkably even. Yet, this very smoothness also raises a tantalizing question about dark matter. If the ultraviolet background has a significant component from dark matter decay, its uniformity would tell us something extraordinary about the nature of dark matter itself. For the glow to be so even, the dark matter particles must be distributed with incredible smoothness throughout the universe. This fits perfectly with our current understanding of cold dark matter, which forms clumpy halos around galaxies but is thought to be distributed much more smoothly on the very largest scales. A uniform UV background could therefore be indirect but powerful evidence that dark matter is indeed cold and non-interacting, just as the leading models propose. The silence of the background, its lack of variation, might be speaking volumes about the silent, invisible component that shapes the cosmos. This unexpected uniformity, therefore, is far from a dull characteristic. It is a deep cosmological clue, forcing us to think about the universe not as a collection of isolated objects, but as a single, connected entity whose history is written in the subtle, even glow of its hidden light. Now we arrive at a mystery that takes us back to one of the most pivotal chapters in cosmic history, a period so transformative it fundamentally altered the fabric of the universe itself. This is the epoch of reionization, and the cosmic ultraviolet background may hold within it a faint, fossilized echo of that cosmic dawn. To understand this seventh mystery, we need to rewind the clock to a time before stars and galaxies, when the universe was a very different place. In its infancy, the cosmos was a hot, dense soup of particles. As it expanded and cooled, protons and electrons combined to form neutral hydrogen gas, plunging the universe into a kind of dark age. For millions of years, there were no light sources. The universe was filled with an opaque fog of this neutral hydrogen, blocking the passage of any light that might try to travel through it. Then something extraordinary happened. The first stars and galaxies ignited, and they were unlike anything that followed. These primordial objects burned incredibly hot, flooding their surroundings with intense ultraviolet radiation. This radiation had enough energy to rip electrons away from the neutral hydrogen atoms, reionizing the gas and over hundreds of millions of years burning away the cosmic fog. This was the epoch of reionization, the moment the universe became transparent, a necessary step that allowed light to travel freely across space and billions of years later into our telescopes. The cosmic ultraviolet background is intimately linked to this event. The very first photons that contributed to this background were the ones responsible for reionization. They were the ultraviolet photons that escaped from those first galaxies and began the process of clearing the fog. The idea, then, is that the CUVB might contain a residual signal from this ancient era, a kind of echo of that first great illumination. It would be the accumulated light from the very sources that engineered one of the most significant phase transitions the universe has ever undergone. If we could isolate this specific component, it would be like finding a recording of the universe's birth of light, giving us a direct window into the properties and distribution of those first elusive stars and galaxies. The challenge, however, is monumental. It's an exercise in cosmic archaeology, trying to uncover the foundations of a city by sifting through layers of rubble and modern construction. The signal from the reionization era is incredibly ancient and faint. Since it began, the universe has been continuously producing ultraviolet light from countless subsequent generations of stars. The light from these more recent sources completely dominates the cosmic ultraviolet background we measure today. Trying to find the specific contribution from the first stars is like trying to hear the first quiet note of a symphony after the entire orchestra has been playing at full volume for hours. The recent emissions are simply louder and more abundant, drowning out the primordial signal. To make matters even more complex, the process of reionization itself was not a single, instantaneous flash. It was a gradual and messy process. Ionized bubbles formed around the first clusters of stars and galaxies, like lakes of clarity in the opaque fog. These bubbles grew and eventually overlapped. The ultraviolet light from this era would not have been a smooth, uniform signal. It would have been patchy, reflecting the uneven progress of reionization across the cosmos. As this light has traveled for billions of years, the expansion of the universe has stretched its wavelength and blurred its features, but some imprint of that initial patchiness might still remain hidden within the background's statistical properties. Detecting that subtle anisotropy, that faint unevenness, is one of the holy grails of modern cosmology, as it would provide a direct map of how and where the first structures lit up the darkness. Scientists are employing sophisticated statistical techniques and computer simulations to tackle this problem. They create detailed models of the reionization process, predicting what the ultraviolet background should have looked like at that time. They then model how that light would be processed, stretched, and mixed with light from later epochs as it journeys to us. By comparing these intricate predictions with the actual, all-sky maps of the CUVB, they hunt for discrepancies or patterns that align with the reionization models. It's a painstaking process of matching a hypothetical fingerprint to a faded and overwritten document. The James Webb Space Telescope is providing crucial new data by directly observing some of the earliest galaxies, helping to constrain the models of what those first light sources were actually like. Every new piece of information about the early universe helps to refine the search for this ultimate echo, bringing us closer to hearing the faint but momentous sound of the cosmos opening its eyes for the first time. Moving from the faint echoes of the universe's first dawn, we encounter a source of light so brilliant it can outshine entire galaxies, the quasar. These cosmic powerhouses sit at the heart of distant galaxies, fueled by supermassive black holes consuming vast amounts of gas and dust. As matter spirals into the gravitational abyss, it heats to incredible temperatures, releasing a torrent of radiation across the electromagnetic spectrum, with a significant portion of its energy blazing forth in the ultraviolet. Given their sheer luminosity, it seems almost certain that quasars must be major players in creating the cosmic ultraviolet background. Yet, pinning down their exact contribution has sparked one of the most enduring controversies in the field, a debate that hinges on a fundamental question of perspective. The initial logic was straightforward. If you want to know how much light quasars contribute to the diffuse glow, you simply count them. Astronomers would conduct deep surveys, cataloging quasars across the sky and measuring their individual brightness. They would then add up all this light, much like calculating the total wattage of every light bulb in a city to understand its overall brightness. The results of these tallies, however, led to a puzzling conclusion. The combined ultraviolet light from all the known quasars fell significantly short of what would be needed to explain a large portion of the background glow. It was as if you had counted every street lamp and window in the metropolis, but their total light only accounted for a small fraction of the observed haze hanging over the city. This quasar shortfall suggested that either quasars were not the dominant source we thought they were, or our census of them was fundamentally flawed. This is where the controversy truly ignites, centered on a fascinating and peculiar property of quasars known as beaming. The intense radiation from a quasar is not emitted evenly in all directions like a simple light bulb. Instead, it is funneled and concentrated into powerful jets that shoot out from the poles of the accretion disk, the swirling platter of material feeding the black hole. This means a quasar's brightness is not a fixed property. It depends drastically on your angle of view. If you happen to be looking straight down the barrel of one of these jets, the quasar will appear phenomenally bright. But if you are viewing it from the side, from an angle where the beamed light is not pointing at you, the same object can appear hundreds or even thousands of times fainter. We on Earth can only see the quasars whose beams are pointed in our general direction. The rest, the vast majority, remain hidden from our view, their ultraviolet light invisible to our telescopes. This beaming effect creates a monumental challenge for astronomers trying to assess the quasar contribution. Our census is inherently biased. We have an accurate count of the tip of the iceberg, the quasars pointed directly at us, but we are largely blind to the much larger population of misaligned quasars. The critical question becomes, how much ultraviolet light are these hidden quasars producing? If their faint, sideways glow is still significant, then we might be drastically underestimating their total impact on the background. Their combined, unresolved light could very well be the missing piece of the puzzle. On the other hand, if the beaming is so extreme that quasars viewed from the side are truly dim, then our initial estimates might be correct, and we must look elsewhere for the source of the glow. Resolving this debate requires clever indirect methods. One approach is to look for the shadows cast by these hidden quasars. Scientists search for distant clouds of hydrogen gas that are being illuminated by the intense radiation from a quasar, even if we cannot see the quasar itself directly. It's like deducing the presence of a hidden spotlight by seeing its glow reflected off a nearby wall. Another method involves studying the galaxies that host these active black holes. By observing the properties of the host galaxy from different angles, astronomers can infer the presence and orientation of a central quasar, even when its brilliant beacon is not pointed our way. These techniques are slowly painting a more complete picture, suggesting that the population of hidden quasars is indeed substantial. However, quantifying their total ultraviolet output with enough precision to settle the controversy remains an active and difficult frontier of research. The quasar contribution controversy is a powerful reminder that in astronomy, what you see is not always what you get, and that the universe's most brilliant objects might be hiding their true numbers and their true power in plain sight. Now, let's shift our focus from the brilliance of quasars to a far more subtle and ghostly phenomenon occurring within the largest gravitationally bound structures in the universe, galaxy clusters. These clusters are cosmic metropolises containing hundreds or even thousands of galaxies all swarming together. But the galaxies themselves are not the entire story. In the immense spaces between them, a faint diffuse light persists, a glow known as intracluster light. This is our ninth mystery, and it asks a haunting question. Could the combined light from countless stars that have been ripped from their homes and now drift eternally in intergalactic space be a hidden contributor to the cosmic ultraviolet background? The origin of this ghostly glow is a tale of cosmic violence on a grand scale. Within a dense galaxy cluster, galaxies are not serene islands. They are constantly interacting, swinging past one another at tremendous speeds. During these close encounters, their immense gravitational fields act like tidal forces, pulling and stretching each other. This gravitational tug of war can be so violent that it literally plucks stars right out of their host galaxies. These stars are flung into the dark, empty spaces between the galaxies, becoming permanent exiles, wandering the vast intracluster medium. Over billions of years, as countless galactic interactions occur, a huge population of these orphan stars builds up, creating a faint, pervasive fog of starlight that fills the entire cluster. While most of this light is in the visible spectrum, hot, young, massive stars, the kind that emit copious ultraviolet light, can also be found among this population. either from recent star formation in tidal tails or from stars that were ejected while still in their brilliant, short-lived youth. Measuring this intracluster light, especially its ultraviolet component, is an extraordinary technical challenge. It is incredibly faint, often thousands of times dimmer than the natural glow of our own night sky. Trying to detect it is like trying to spot a single lit match from an airplane flying over a brightly lit city at night. Astronomers must use extremely sensitive detectors on the world's most powerful telescopes and employ sophisticated image processing techniques to carefully subtract the light from every single galaxy and every foreground star, and then even subtract the airglow from Earth's own atmosphere. What remains, if done perfectly, is the subtle, smooth glow of the intracluster stars. Isolating just the ultraviolet part of this already faint signal is even more difficult, pushing our observational capabilities to their absolute limit. The central question is whether the combined ultraviolet output from all the intracluster stars in all the galaxy clusters across the universe could add up to a significant portion of the unresolved cosmic ultraviolet background. On the one hand, the sheer volume of space within clusters is enormous. If each cluster contains a vast halo of these orphan stars, their collective light could be substantial. Some estimates suggest that in massive clusters, intracluster light can account for a significant percentage of the total starlight. If this is typical, then when we look at the sky and see a diffuse UV glow, we might be seeing, in part, the accumulated light from trillions of lost suns, shining faintly from the darkest, most empty regions of the cosmos. On the other hand, there are strong reasons to be skeptical. Galaxy clusters, while immense, are relatively rare structures in the universe. The vast majority of space is occupied by the even larger cosmic voids where the density of galaxies, and thus the number of orphan stars, is virtually zero. For intracluster light to make a major contribution to a background that is uniform across the entire sky, the distribution of these orphan stars would have to be far more widespread than we currently believe. Furthermore, the stars that get ejected into intracluster space are typically older, redder stars. The violent processes that strip stars from galaxies tend to preferentially remove the outer, older stellar populations. The hot, young, UV-bright stars are more commonly found in the dense central regions of galaxies and are less likely to be torn away. So, while intracluster light is a fascinating and real phenomenon, its spectral signature might be too red, lacking the necessary ultraviolet intensity to explain the specific glow we're investigating. This mystery forces us to consider the cosmos not just as a collection of galaxies, but as a dynamic ecosystem where stars themselves can become unmoored from their galactic anchors. Whether these lost stars are a major source of the ultraviolet background or not, their existence reminds us that the boundaries of galaxies are not rigid walls. They are fluid and permeable, and the space between them is not entirely empty, but sprinkled with the faint, wandering embers of cosmic encounters that have shaped the universe over billions of years. But beyond its sheer intensity and puzzling uniformity, the cosmic ultraviolet background holds another, more subtle clue: its distinctive color. Just as white light can be split by a prism into a rainbow of different hues, the CUVB can be broken down into its component wavelengths, creating a spectrum. This spectrum is like a unique fingerprint, revealing the energy and characteristics of the sources that created it. And this is where we encounter our 10th mystery, the spectral shape anomaly. Simply put, the color of this background light doesn't match what we'd expect if it were simply the combined light of all the galaxies and quasars we know about. It's as if you meticulously measured the paint from every known artist's tube in a studio, mixed them all together, and instead of getting the expected shade of brown, you got a color with a strange, unexpected tint. Something is off, and that discrepancy points to either sources we haven't yet imagined or physical processes we don't fully understand. To grasp why this spectral shape is so telling, think about what makes different celestial objects glow with different colors. A hot, young, massive star burns at tens of thousands of degrees, emitting most of its energy in high-energy, short-wavelength ultraviolet light. Its spectrum will be dominated by these blazing blue and UV hues. An older population of stars, like those in an elliptical galaxy, is cooler and redder. Its spectrum would peak at longer wavelengths. A quasar, powered by a supermassive black hole, has a very different spectral signature altogether, often with a broad, flat continuum of light across the UV and visible range. So, when astronomers want to test the hypothesis that the CUVB is just the sum of all known sources, they perform a massive cosmic calculation. They take the observed spectra of every type of galaxy and quasar, factor in how many of each exist across cosmic time, and simulate what their combined redshifted light should look like when it reaches us. They create a predicted spectrum for the background. When they compare this sophisticated prediction to the actual, measured spectrum of the cosmic ultraviolet background, they find a consistent and puzzling mismatch. The real background is softer than expected. It has a relative deficit of the highest energy, shortest wavelength ultraviolet photons and a relative excess of lower energy UV light. It's not a huge difference, but in the precise world of astrophysics, even a small anomaly can signal a major oversight. This is the spectral shape anomaly. The mixed light of the universe has a color temperature that is slightly off, suggesting that our inventory of cosmic light bulbs is either incomplete or that the light has been tampered with on its long journey through space. This leads to two broad categories of explanation. The first possibility is that we are missing an entire class of ultraviolet sources. Perhaps the universe is filled with objects that are intrinsically softer emitters than the typical galaxies and quasars in our catalogues. What could these be? One intriguing candidate is a population of low-mass, low-metallicity galaxies. Metallicity is the astronomer's term for elements heavier than hydrogen and helium. In the early universe, before many stars had lived and died, enriching space with these heavy elements, stars could form with very different characteristics. They might be less hot and massive on average, producing a gentler, less harsh ultraviolet glow. If such galaxies are far more numerous than we currently believe, their collective light could shift the overall spectrum of the background toward the redder, softer end of the UV range. We simply haven't found enough of them yet to account for their influence. The second, and perhaps more complex, possibility is that the light from known sources is being systematically altered before it reaches us. The journey of a UV photon across billions of light years is perilous. We've already discussed the filtering effect of the Lyman-alpha forest, but this process is wavelength dependent. The intergalactic medium is much more effective at absorbing the very highest energy UV photons. As these photons travel, they have a higher probability of encountering a neutral hydrogen atom and being absorbed. This process, known as Lyman continuum absorption, acts like a cosmic filter that preferentially removes the bluest UV light, naturally reddening the overall spectrum. The question then becomes, is the observed softening of the CUVB spectrum exactly what we'd expect from this filtering, or is it even more pronounced? If it's more pronounced, it suggests that the intrinsic spectrum of the sources was even bluer than we think, pointing back to the existence of those hot, early stars. But if the filtering alone can explain the anomaly, it would be a powerful confirmation of our models of the intergalactic medium. Unraveling this spectral mystery requires incredibly precise measurements from space-based telescopes and equally sophisticated computer modeling. It's a delicate balancing act between the properties of the emitters and the properties of the cosmic medium they shine through. Each new observation of distant galaxies and quasars helps refine our understanding of their intrinsic spectra. Each new map of the Lyman-alpha forest helps us understand the filtering process. By iterating between these two sides of the equation, astronomers hope to finally account for the unusual color of the universe's diffuse ultraviolet glow. Solving the spectral shape anomaly isn't just about fixing a minor discrepancy in a graph. It's about achieving a consistent and complete picture of the cosmic energy budget from the first stars to the present day, and understanding all the obstacles that light faces on its epic journey across the cosmos. This journey into the source of the ultraviolet background inevitably leads us to a question of cosmic history. We've been treating the glow as a static picture, but the universe is a dynamic film constantly changing. This brings us to our 11th mystery, the time evolution puzzle. How is the intensity of this background expected to change as we look back in time, and does reality match our expectations? The answer reveals a startling disconnect between our theoretical models of galaxy evolution and the actual story written in the light. Think of the universe's history as a timeline. At the far end, close to the Big Bang, there's the Dark Age, followed by the epoch of reionization where the first stars and galaxies switch on. We'd naturally expect the cosmic ultraviolet background to be very faint at this point, just a few flickers in the vast darkness. Then, as the universe matures over billions of years, galaxy formation should hit a peak. Vast quantities of gas collapse to form stars, and quasars ignite, flooding the cosmos with ultraviolet radiation. We'd predict that the background glow would grow steadily brighter, reaching a brilliant peak during this cosmic high noon of star formation. Finally, as the universe ages further and the raw fuel for new stars is depleted, the rate of star birth should decline. The background, in turn, should gradually fade like the dying embers of a great fire. This rise and fall is the fundamental prediction, a cosmic heartbeat that should be imprinted on the ultraviolet background. To test this, astronomers use a powerful tool, redshift, because light takes time to travel. Looking at greater distances means looking further back in time. By measuring the intensity of the ultraviolet background at different redshifts, we can effectively create a movie of its evolution. Sophisticated computer simulations, which model the birth, life, and death of millions of galaxies across cosmic history, provide a predicted script for this movie. They tell us how bright the background should be at every epoch. When we compare this script to the actual observations, however, the plot thickens dramatically. The discrepancies are profound. In some eras, particularly the early universe just after reionization, the measured background is significantly brighter than the simulations predict. It's as if the cosmic dawn was far more brilliant than our models ever allowed for, suggesting that early galaxies were either more numerous, more efficient at producing ultraviolet light, or both. Our theories might be underestimating the sheer productive power of the infant cosmos. Then, at other points in cosmic history, the opposite problem occurs. At redshifts corresponding to the universe's middle age, around the expected peak of star formation, the background sometimes appears fainter than anticipated. This implies that the total ultraviolet output from all galaxies during this busy period was less than we calculated. Perhaps galactic feedback, the powerful winds from supernova and black holes that can blow gas away and shut down star formation, is more effective than we thought, putting a lid on the peak brightness. Or maybe dust, which blocks ultraviolet light, became widespread more quickly than our models account for, dimming the true intensity of the cosmic noon. These mismatches are not minor accounting errors, they are fundamental clues. They tell us that our understanding of how galaxies evolve over time is incomplete. The simulations are built on our best theories about gas cooling, star formation, and feedback mechanisms. When the predicted evolution of the ultraviolet background fails to match the observed data, it's a clear sign that one or more of these underlying physics ingredients is wrong. For instance, the early excess of UV light might mean that the first galaxies formed stars in bursts that were more intense and rapid than we simulate. The later dimming could indicate that we don't fully understand how galaxies self-regulate, how they exhaust their fuel supply, or how they become shrouded in dust. Solving the time evolution puzzle is therefore a primary driver for improving our models of galaxy formation. Each new observation of the background's intensity at a specific redshift acts as a critical checkpoint. Theorists must adjust their simulations, tweaking the rules for how stars are born and how they influence their surroundings, until the virtual universe produces an ultraviolet background that matches the real one across all of cosmic time. It's a painstaking process of calibration, where the faint, diffuse glow of the CUVB serves as a master metric for testing our entire narrative of cosmic history. The puzzle reminds us that the universe's story is still being written, and its light holds the key to reading the chapters we have yet to fully understand. Now we venture into a realm where the invisible violence of the cosmos might be painting the sky with light. This brings us to our 12th mystery, a highly speculative but fascinating possibility: the connection between the cosmic ultraviolet background and high-energy cosmic rays. These are not rays of light, but rather atomic nuclei, protons, and heavier elements that have been accelerated to nearly the speed of light by some of the universe's most powerful engines, like supernova remnants and the jets of active galaxies. As these microscopic bullets tear through space, they could, through their interactions, be responsible for generating a portion of the very UV glow we are trying to explain. To understand how this might work, picture a cosmic ray proton, a particle smaller than an atom, carrying the energy of a professionally thrown fastball. It's traveling so fast that it's a blur of concentrated energy. Now, imagine this proton slamming into a stationary atom of hydrogen gas floating in the vast intergalactic medium. The collision is tremendously violent. The proton can rip the electron right off the hydrogen atom, a process known as ionization, but the interaction doesn't stop there. The crash can also excite the atom, causing its remaining electron to jump to a higher energy level. When that electron falls back down to its normal state, it releases the excess energy in the form of a photon of light. And for hydrogen, a significant portion of that light is emitted at the specific ultraviolet wavelength we call Lyman-alpha. In essence, the immense kinetic energy of the cosmic ray is converted, through this chain of events, into ultraviolet photons. It's a bit like striking a match by throwing a rock at it. The impact itself creates the spark. This process isn't just theoretical. We observe it happening on a smaller scale within our own galaxy. In regions where cosmic rays are known to be dense, such as around supernova remnants, astronomers can detect a faint glow of light produced by these very interactions. The question for cosmologists is whether this same mechanism, operating on a universe-wide scale, could be significant enough to contribute to the diffuse cosmic ultraviolet background. Could the combined effect of trillions upon trillions of these microscopic collisions, occurring in the near vacuum between galaxies over billions of years, produce a detectable, integrated glow? The challenge in answering this lies in the incredible diffuseness of both the cosmic rays and the intergalactic gas. Within a galaxy, the density of gas is high enough that these collisions are relatively frequent. But in the intergalactic void, the gas is so thin that a cosmic ray particle could travel for millions of years before hitting anything. To produce a substantial amount of light, you would need a truly enormous flux of cosmic rays permeating all of space. Some theories suggest that the vast magnetic fields that thread through the cosmic web could act as containment vessels, trapping cosmic rays and keeping their density high enough in the filaments of the web for this process to be effective. If these fields are strong and pervasive, the entire universe might be gently glowing with the faint ultraviolet light of constant, low-level particle collisions. However, most astronomers consider this a secondary or even negligible contributor to the overall background. The primary reason is efficiency. Converting the energy of a high-speed proton into a single ultraviolet photon is an incredibly inefficient process. Most of the proton's energy in a collision goes into heating the gas or creating other particles, with only a tiny fraction emerging as the specific UV light we're interested in. For cosmic ray interactions to account for a substantial part of the mysterious glow, the universe would have to be far more saturated with these high-energy particles than our current observations suggest. While cosmic rays are a crucial part of the cosmic ecosystem, their energy density appears to be orders of magnitude too low to compete with the direct starlight from galaxies or the more exotic possibilities like dark matter decay. Yet the idea remains compelling because it connects two great cosmic puzzles. The origin of the highest energy cosmic rays is itself a major mystery. By considering their potential role in the ultraviolet background, we are forced to think about the total energy budget of the universe in a holistic way. It reminds us that the cosmos is a complex system of energy transfer, where the violent, high-energy phenomena and the quiet, diffuse glows are all part of the same interconnected story. While it may not be the leading solution, this speculative link underscores a fundamental principle of science. Sometimes, the path to solving one mystery involves following a thread that leads to another, revealing the beautiful and often unexpected connections that weave the fabric of the universe together. As we attempt to peer into the deepest reaches of the cosmos, our greatest obstacle often lies much closer to home, woven into the very fabric of our celestial neighborhood. This is the Galactic Foreground Challenge, a monumental task of cosmic subtraction that stands between our telescopes and the faint whisper of the extragalactic ultraviolet background. To understand why this is so difficult, we need to recognize that our solar system is embedded within a galaxy that is itself brilliantly aglow with ultraviolet light. The Milky Way is not a transparent window. It is a brilliant, shimmering curtain of light that we must see through, and carefully removing its contribution is as much an art as it is a science. The sources of this interfering glare are twofold, each presenting its own unique complications. First, there are the hot, young, massive stars scattered throughout the galactic disk. These stellar powerhouses burn at extraordinary temperatures, and as a result, they flood their surroundings with intense ultraviolet radiation. From our vantage point inside the galaxy, this starlight appears not as distinct points, but often as a diffuse, hazy glow, especially when reflected off of the second major component, interstellar dust. This dust, composed of tiny grains of carbon and silicate, is pervasive throughout the Milky Way. While it efficiently absorbs ultraviolet light, it doesn't just make things darker. It re-radiates that energy, scattering it in all directions and creating a complex, nebulous background of its own. So, when an astronomer points a UV telescope at what should be a dark patch of extragalactic space, the detector is flooded with this combined light from our galaxy's stars and its illuminated dust. This foreground is not a faint nuisance. It can be hundreds or even thousands of times brighter than the elusive cosmic ultraviolet background we are trying to measure. Isolating the extragalactic signal is like trying to hear a single whispered conversation from across a crowded, roaring stadium. The process of removing this galactic foreground is a meticulous and fraught undertaking. It begins with creating a detailed model of the Milky Way's ultraviolet emission. Scientists use data from missions like the Galaxy Evolution Explorer or GALEX, which map the entire sky in ultraviolet light. They analyze how the brightness and color of this emission change from one region to another, correlating it with maps of interstellar dust and the known positions of hot stars. The goal is to build a predictive formula. If you know the density of dust and the number of hot stars in a given direction, the model should be able to tell you exactly how much foreground UV light to expect. Once this model is built, astronomers subtract its prediction from the total light measured in that direction. In principle, what remains should be the pristine light from beyond our galaxy. In practice, however, this subtraction process is a minefield of uncertainty. The models are based on our best understanding of how dust scatters and absorbs light, but that understanding is imperfect. The properties of interstellar dust grains can vary from one cloud to another, meaning the scattering efficiency might be slightly different in the patch of sky you're studying compared to the region you used to calibrate your model. A small error in the model when applied across the entire sky can lead to a significant over or under subtraction of the foreground. If you subtract too much, you artificially create a dip or a mysterious dark patch in the cosmic background. If you subtract too little, you might mistake a localized fluctuation in the Milky Way's own glow for a genuine feature of the extragalactic signal. This uncertainty is the ghost in the machine, a source of potential error that can either create illusory mysteries or hide real ones lurking just beneath the surface of the data. The consequence of this challenge is that some of the apparent anomalies or features in the cosmic ultraviolet background might not be cosmic at all. They could be artifacts of our imperfect cleaning process. A reported fluctuation in the background's smoothness, for instance, might simply reflect an undiscovered variation in the properties of a nearby interstellar dust cloud. This forces a level of humility in the interpretation of the data. Before claiming a discovery about the large-scale structure of the universe, scientists must first perform a painstaking audit of their own galactic backyard, ensuring that the signal they're seeing isn't just a reflection of local interstellar weather. The quest to understand the most distant universe is therefore inextricably linked to the ongoing effort to map and comprehend our own galactic home. A reminder that sometimes to see the forest, you must first correctly account for every tree right in front of you. Even as we grapple with the challenges of our own galactic neighborhood, a far more pervasive and enigmatic filter complicates our view of the distant universe, cosmic dust. This brings us to our 14th mystery, the dust extinction enigma. The term extinction in astronomy doesn't mean annihilation. It refers to the dimming and reddening of light as it passes through clouds of tiny solid particles. This dust, forged in the furnaces of dying stars and scattered across galaxies and intergalactic space, acts as a universal veil. It doesn't just block ultraviolet light, it transforms it, and our imperfect understanding of this transformation introduces one of the largest sources of uncertainty in our entire quest to understand the cosmic ultraviolet background. To appreciate the scale of this problem, imagine you're trying to measure the true wattage of a light bulb, but it's hidden inside a lamp with a thick, sooty shade. You can see some of the light that manages to penetrate the shade, but most of the bulb's energy is absorbed by the fabric, heating it up. The shade itself then glows with a dull red heat. This is precisely what happens on a cosmic scale. Hot, young stars are brilliant ultraviolet light bulbs. The dust that surrounds them acts as the lamp shade, absorbing that high-energy UV radiation. The dust grains heat up and re-radiate the energy, but at much longer, lower energy wavelengths, primarily in the infrared part of the spectrum. So, a significant portion of the ultraviolet light that stars produce never escapes its host galaxy. It is effectively converted into infrared light. When we try to calculate the true, intrinsic ultraviolet output of the early universe to see if it can account for the background glow, we must first correct for this universal dimming. We have to estimate how much UV light has been lost to dust extinction. The enigma lies in the fact that we cannot know the properties of this cosmic dust with perfect precision, especially when looking back billions of years. The efficiency with which dust extinguishes light depends on several factors: the size of the dust grains, their chemical composition, and their shape. Are they mostly large grains or tiny specks? Are they rich in carbon, like soot, or in silicates, like fine sand? Modern dust in nearby galaxies has been well studied, and we have a standard law called the extinction law that describes how it dims different colors of light. We know that dust typically reddens light, meaning it blocks blue and ultraviolet light more effectively than red light. But can we assume that the dust in the earliest galaxies, which formed from the first heavy elements created in the universe, had the same properties? Almost certainly not. The first dust grains were likely more primitive, composed of different materials and having a different size distribution, which would mean they dimmed and reddened starlight in a way that is alien to our modern experience. This uncertainty creates a vast range of possibilities. If the dust in early galaxies was less effective at blocking ultraviolet light, then the correction we apply is small. This would mean the stars we see are nearly as bright as they truly are, and their combined light might be sufficient to explain the cosmic ultraviolet background without needing exotic sources. However, if the early universe was surprisingly dusty, if those first generations of stars polluted their surroundings with heavy elements and dust very quickly, then the correction factor becomes enormous. We would have to conclude that the true ultraviolet luminosity of the early cosmos was staggeringly high, far beyond what we directly observe. In this scenario, there could have been a truly immense amount of ultraviolet light produced that we cannot see because it was immediately absorbed and converted to infrared. The unresolved background glow we measure today would then be just the faint, leaked remnant of a once far more brilliant cosmic dawn, a ghost of its former intensity. The difference between these two scenarios is not a minor adjustment. It can change the calculated energy output of the entire young universe by an order of magnitude or more. Complicating matters further is the potential for dust to exist not just within galaxies, but also in the intergalactic medium itself. While the IGM is a near-perfect vacuum by Earth standards, even a tiny amount of dust spread across the vast volumes of intergalactic space could have a cumulative filtering effect. If the cosmic web is threaded with fine filaments of dust, perhaps ejected from galaxies by powerful winds, then the ultraviolet background light would be dimmed and reddened a second time on its long journey to our telescopes. This intergalactic dust extinction would be in addition to the extinction that occurred within the source galaxies themselves. Detecting this diffuse intergalactic dust is incredibly difficult, as its signature is subtle and blended with the effects of the gaseous Lyman-alpha forest. Yet, if it exists, it would mean our view of the ultraviolet universe is even more obscured than we currently imagine, and the true sources of the background must be correspondingly brighter and more powerful. The quest to solve the dust extinction enigma is therefore a parallel investigation into the history of cosmic pollution. Astronomers are using the James Webb Space Telescope's extraordinary sensitivity in the infrared to peer through the dust. By observing the same early galaxies in both ultraviolet light, which is redshifted into the visible and infrared, and in the far infrared light emitted by the warm dust itself, they can begin to measure the extinction directly for individual galaxies. They can compare the amount of light that escaped in the UV to the amount that was absorbed and re-radiated in the IR, building a census of dustiness across cosmic time. Each new data point helps to constrain the properties of early dust, gradually replacing our assumptions with direct measurements. Until that picture is complete, the dust extinction enigma remains a formidable fog bank in our cosmological models, a reminder that to see the light of the cosmos clearly, we must first learn to fully account for the shadows cast by its darkest, most minute particles. Of all the potential sources we've considered, none carries quite the same profound weight as the very first stars. These are not just another population of galaxies. They are the mythical pioneers of the cosmos, the ones that ended the universe's dark ages and lit the fuse for everything that would follow. This brings us to the 15th mystery, a hypothesis that reaches back to the very beginning of light itself, the role of population 3 stars. The name sounds technical, but the concept is breathtaking. These would have been the universe's first true stars, and if their faint collective glow is indeed woven into the cosmic ultraviolet background, we would be gazing upon a fossilized echo of creation's first dawn. To understand why these stars are so special, we have to picture the universe before they existed. It was a simple place composed almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang. There were no heavier elements like carbon, oxygen, or iron. This elemental purity had a dramatic effect on the stars that could form. Without heavy elements to help the gas clouds cool and fragment efficiently, the first clumps of matter that collapsed under gravity were enormous. The result, scientists believe, were stars of almost unimaginable scale, behemoths that could be hundreds of times more massive than our Sun. These are the hypothetical population 3 stars. They would have burned at ferociously high temperatures, making them incredibly luminous and flooding their surroundings with intense ultraviolet radiation. Their lives were as brilliant as they were brief, ending in cataclysmic supernova after only a few million years, seeding the cosmos with the first heavy elements that would become the building blocks for future stars, planets, and life itself. The connection to the cosmic ultraviolet background is direct and compelling. If these first stars were as massive, hot, and numerous as theories suggest, their combined ultraviolet output would have been staggering. It would have been the primary driver of the reionization process, the event that burned away the primordial fog of neutral hydrogen. The idea is that the faint, uniform glow we detect today could contain the redshifted and diluted remnant of that initial, universe-wide flash of starlight. It would be the ultimate cosmic fossil, a background hum left over from the moment the cosmos first switched on its lights. Detecting this specific signature would be like finding a recording of the Big Bang's aftermath, providing an unparalleled window into the conditions of the infant universe. The challenge, however, is that finding direct, incontrovertible evidence for a single population 3 star has so far been impossible. They lived and died so quickly that even our most powerful telescopes, like the James Webb Space Telescope, are unlikely to ever resolve one individually. Their light is too faint and has been stretched too far into the infrared by the expansion of the universe. So, astronomers are forced to hunt for their indirect signature, and the cosmic ultraviolet background is one of the most promising places to look. The strategy is to create incredibly detailed computer simulations of the early universe, modeling the formation and evolution of these first stars. These simulations predict the specific spectral fingerprint that a population of such hot, massive stars would have imprinted on the ultraviolet background. It's a unique pattern of intensity across different wavelengths, a subtle color difference that would distinguish it from the light produced by later generations of stars. The search then becomes a monumental exercise in cosmic forensics. Scientists take the actual, all-sky map of the CUVB and carefully subtract every other known or suspected contributor. They remove the light from all the resolved galaxies. They model and subtract the quasar contribution. They account for the various other potential sources we've discussed. What they hope to find is a residual signal that stubbornly remains, and that matches the predicted spectral signature of population 3 stars. It's a bit like trying to identify a specific instrument in a symphony by silencing all the others one by one, hoping to hear the distinct, lingering note of a single ancient flute. The reason this is so exceptionally challenging is that the signal, if it exists, is extraordinarily faint and buried under a mountain of brighter, more recent light. Furthermore, there is significant debate about the properties of these first stars. Were they all truly monstrous in size? Did they form in isolation or in dense clusters? How quickly did they pollute their surroundings with the heavy elements from their supernova, thereby changing the conditions for the next generation of stars? Each variation in these properties changes the predicted spectral signature. A universe filled with 500 solar mass stars would leave a different ultraviolet fingerprint than one filled with 100 solar mass stars. The hunt is therefore not for one specific signal, but for a signal that falls within a range of possibilities. It requires a delicate interplay between the theorists refining their models and the observers pushing the limits of detection, each new piece of data helping to narrow the search. The ongoing quest to find the ghost of population 3 stars within the cosmic ultraviolet background is more than just solving one mystery. It is an attempt to touch the origin of starlight itself, to confirm the existence of the celestial giants that gave rise to the rich and complex universe we inhabit today. While the furious birth of stars is a primary source of a galaxy's light, the most powerful energy source in the universe often acts to suppress that very process in a dramatic cosmic balancing act known as feedback. This brings us to our 16th mystery, the search for the IGM feedback signature within the cosmic ultraviolet background. At the heart of many large galaxies lies an active galactic nucleus, or AN, a supermassive black hole that is actively feeding. As vast quantities of gas spiral inwards, the region around the black hole shines with an intensity that can outshine the billions of stars in the host galaxy. But this isn't just a brilliant beacon, it's also a cosmic engine that profoundly shapes its surroundings. The immense radiation and powerful jets blasting from the IGM can drive colossal winds, pushing gas and dust out of the galaxy at speeds of thousands of kilometers per second. This process effectively blows away the very fuel required for future star formation, putting a brake on the galaxy's growth. It's a form of self-regulation where the central black hole prevents the galaxy from becoming too large by cutting off its gas supply. The connection to our mystery lies in what happens to this ejected material. As the hurricane force winds from the IGM slam into the surrounding interstellar and intergalactic medium, they don't just vanish. The gases shock heated to extreme temperatures, millions of degrees. While much of this superheated gas glows in X-rays, the cooler outer layers and the vast inflated bubbles it creates can radiate copiously in the ultraviolet. Theoretical models suggest that over time, a galaxy undergoing repeated episodes of IGM feedback could become encased in a gigantic, hot halo of diffused gas, a cosmic atmosphere shining faintly in UV light. Since IGM activity is thought to be a common phase in the life of most large galaxies, the combined glow from all these individual halos spread across the universe could potentially contribute a significant component to the diffuse cosmic ultraviolet background. The background glow wouldn't just be the light of creation from stars, it would also be the energetic signature of destruction and regulation from black holes. Detecting this specific signature, however, is a monumental challenge. The primary issue is one of distinction. How do you separate the ultraviolet light coming from a galaxy's hot halo, created by IGM feedback, from the light of the galaxy's own stars? From our distant vantage point, the two sources are blurred together. The halo's glow is incredibly faint compared to the brilliant core of the galaxy. It's like trying to see the faint, warm glow of a light bulb's heated glass shade from miles away when the bulb's filament itself is blazingly bright. Astronomers have to use sophisticated techniques to model and subtract the starlight from the galaxy's main body, hoping to detect an residual, extended ultraviolet halo. In a few nearby galaxies, hints of such structures have been found, but confirming they are directly tied to IGM feedback and not to other processes like stellar winds is difficult. The search becomes even more complex when we consider the cosmic background. To claim that IGM feedback leaves an imprint on the diffuse glow, we would need to see a statistical correlation. We would need to demonstrate that the parts of the sky with a higher density of galaxies that have, or have had, active nuclei show a slightly stronger ultraviolet background signal. But given the uniformity of the background, this is an exceptionally subtle effect to measure. Furthermore, the feedback process is not constant. It occurs in violent outbursts that may last for millions of years, but that is a short timescale compared to the age of the universe. The hot halo around a galaxy will eventually cool and fade, so the contribution to the background might be intermittent, making it even harder to pin down as a steady, pervasive component. The significance of solving this mystery goes far beyond simply accounting for another source of light. If we could definitively detect the IGM feedback signature in the cosmic ultraviolet background, it would be a powerful validation of one of the key theories of modern cosmology. It would provide direct observational evidence that the growth of supermassive black holes and the growth of galaxies are intimately linked through this feedback mechanism. It would show that the diffuse light filling the cosmos is not just a passive record of stars being born, but an active chronicle of the violent processes that shape and constrain them. The faint ultraviolet glow would then tell a more complete story, a tale of cosmic construction and demolition happening simultaneously, with the most destructive forces in the universe ultimately serving to bring balance and order to the largest structures we know. While the search for the IGM feedback signature highlights the violent interactions within and around galaxies, our next mystery takes us into the truly empty expanses between these vast structures. We've been thinking of the cosmic voids as near-perfect vacuums, but what if they are not so empty after all? This brings us to the 17th mystery, an elusive component of the cosmic web that could be hiding in plain sight within the ultraviolet background, the warm-hot intergalactic medium, or WIM. For decades, cosmologists have faced a troubling accounting problem. When they tally up all the normal matter, the protons, neutrons, and electrons that make up stars, planets, gas, and dust, they find that nearly half of it is missing. This isn't the mysterious dark matter. This is the regular, baryonic matter that the universe is supposed to be made of. The leading candidate for this missing mass is the WIM, a theorized web of incredibly diffuse, hot gas filaments stretching between galaxies and filling the cosmic voids. Visualizing the WIM requires a shift in perspective. Picture the large-scale structure of the universe not just as galaxies clustered together, but as a colossal sponge. The galaxies are the solid parts of the sponge, while the vast, empty-looking voids are the holes. The WIM is theorized to be the thin, barely perceptible film of water coating the entire inner surface of this sponge. It's everywhere, but in any given spot, it's vanishingly thin. This gas isn't cold. It has been heated to temperatures between 100,000 and 10 million degrees by the gravitational shock waves of collapsing cosmic structures and the intense radiation from galaxies and quasars. At these temperatures, the gas is so energetic that it is almost entirely ionized, meaning it's a seething plasma of atomic nuclei and free electrons. And like any hot gas, it should glow. The challenge, and the reason it remains a mystery, is that its glow is extraordinarily faint. This is where the connection to the cosmic ultraviolet background becomes so compelling. While the hottest parts of the WIM radiate primarily in X-rays, the warmer fringes of these filaments are predicted to emit specific wavelengths of ultraviolet light. As highly ionized oxygen atoms in the gas capture stray electrons, they release energy in the form of extreme ultraviolet photons. If the WIM is as pervasive as theories suggest, then the combined, unresolved light from this process, happening across billions of light-years of space, should be subtly encoded into the diffuse UV glow we measure. Detecting this specific signature would be the ultimate confirmation of the WIM existence, solving the half-a-universe missing matter problem at a stroke. It would prove that the cosmic web is not just a map of where galaxies are. It is a continuous, glowing structure of gas with the galaxies merely glittering at the intersections. The search for this signal, however, is aptly described as searching for a whisper in a hurricane. The predicted ultraviolet emission from the WIM is incredibly weak, thousands of times fainter than the other contributors to the background we've discussed. To make matters worse, it is superimposed on a signal that is already a complex puzzle of its own. Astronomers are not looking for a bright new feature. They are looking for an almost imperceptible excess of light at very specific, subtle wavelengths. It's an effort that pushes the limits of signal processing and requires exquisitely sensitive instruments. The strategy involves looking for these faint spectral lines not in the general background, but in the directions of known large-scale structures. By pointing telescopes along the line of sight where other observations, like galaxy surveys, suggest a dense filament of the cosmic web should exist, scientists hope to see a slight statistical enhancement in the UV signal at the wavelength associated with warm hot gas. It's a painstaking process of stacking data and looking for correlations, a bit like trying to hear a faint echo by listening to the same canyon wall 1,000 times and averaging the results. The implications of successfully detecting the WIM ultraviolet signature would be profound. Beyond simply balancing the cosmic ledger of normal matter, it would give us a complete picture of the ecosystem of the universe. We would understand that the space between galaxies is not a true void, but a dynamic medium that contains the majority of the universe's ordinary substance. This gas is the reservoir from which galaxies form and the repository into which they eject material through winds and explosions. Understanding its distribution and temperature is crucial for modeling the entire life cycle of galaxies. The cosmic ultraviolet background, therefore, might hold the key to mapping this final frontier of ordinary matter, revealing the hidden architecture that connects all the visible structures in the cosmos. The quest to find the WIM whisper is a testament to the lengths we must go to complete our understanding of the universe, proving that even the most diffuse and elusive components leave a trace, if only we have the patience and ingenuity to listen for it. But here we arrive at a mystery that brings us back down to Earth, or more accurately, to the intricate machinery orbiting it. After exploring cosmic voids and the first stars, we must confront a more pragmatic, yet equally profound question. How much of the mystery we've been unraveling is truly out there in the cosmos, and how much is an artifact of the very tools we use to see? This is the 18th mystery, the question of instrumental artifacts. It forces a necessary balance between the thrill of discovery and the rigor of skepticism, reminding us that every measurement is a conversation between the universe and the imperfect instruments we build to listen to it. The challenge begins with a simple, undeniable fact. There is no perfectly clean laboratory in space. Our telescopes, like the Hubble Space Telescope or the pioneering Galaxy Evolution Explorer, are magnificent achievements, but they are not immune to their own internal quirks and the messy environment they operate in. The signal they are trying to detect, the cosmic ultraviolet background, is astonishingly faint. It's like trying to measure the gentle heat of a single candle on the moon while standing on Earth. Any small, systematic error in the instrument can easily produce a signal that mimics or masks the subtle cosmic glow we're searching for. Ruling out these instrumental ghosts is therefore the first and most critical step in any analysis, a process as important as the cosmological interpretation that follows. One of the most persistent challenges is stray light. Imagine you're in a dark room trying to measure the faint glow of a watch dial, but someone has left a door slightly ajar, allowing a sliver of light from a bright hallway to seep in. That sliver of light would contaminate your measurement. In space, the sun is that bright hallway. Even with sophisticated sunshades and baffles designed to block direct sunlight, a tiny amount of light can still scatter off internal structures within the telescope, or even off the dust motes and microscopic imperfections on the optics themselves, eventually finding its way to the detector. This stray light creates a low-level, diffuse background that is entirely local to the telescope. For an instrument designed to measure a diffuse cosmic signal, this is a nightmare scenario. Distinguishing between a uniform glow caused by stray light and a uniform glow from the edge of the universe requires incredibly precise modeling of the telescope's optical path and a deep understanding of how it responds to bright objects just outside its field of view. Then there is the ever-present issue of calibration. A telescope's detectors don't measure brightness in absolute terms. They measure a relative response, a digital count that must be converted into a physical unit of energy. This conversion factor is determined through a painstaking process of calibration, often by observing well-understood standard stars whose brightness is known with great precision. But what if the sensitivity of the detector changes over time? exposure to the harsh radiation of space can slowly degrade the performance of the light-sensitive chips. The filters that isolate the ultraviolet light can also experience subtle changes in their transmission properties. If the calibration is off by even 1% or 2%, that small error, when applied to an entire all-sky map, can translate into a significant miscalculation of the background's intensity. It could make the glow appear artificially bright or, conversely, disguise a real feature by making it seem fainter than it truly is. Ensuring that the calibration is rock solid across the entire lifetime of a mission is a constant battle for engineers and scientists. Furthermore, each telescope has its own unique set of instrumental signatures. The electronics that read out the data from the detector can introduce a low-level noise pattern. The very process of subtracting the dark current the signal a detector produces even when no light is falling on it must be done with extreme care. Any residual noise or pattern left over from this subtraction could be misinterpreted as a real astronomical signal. Scientists go to great lengths to characterize these effects, often by taking control observations while pointing the telescope at supposedly empty regions of space, or by using special operating modes designed to isolate the instrument's own behavior. The history of astronomy is littered with exciting discoveries that later turned out to be nothing more than an unfamiliar quirk of a new instrument. This constant vigilance creates a necessary and healthy tension in the field. On one hand, researchers are driven by the desire to find something new, to push the boundaries and interpret every anomaly as a potential breakthrough. On the other hand, they must be their own most severe critics, systematically dismantling their own results to rule out every possible instrumental cause. It's a process of intellectual honesty that is both frustrating and essential. Before claiming that a faint feature in the ultraviolet background is evidence of dark matter decay or the echoes of population 3 stars, a team must first prove beyond a reasonable doubt that the feature isn't simply a glitch in the voltage readout of a camera 1,000,000 miles away. This back and forth between ambition and skepticism is the engine of reliable scientific progress. It ensures that when a discovery about the cosmic ultraviolet background is finally announced, it has been tested against every earthly explanation, leaving only the truly cosmic one standing. Now we confront a limitation that is not technological but profoundly existential. We have been discussing the cosmic ultraviolet background as if it were a single, definitive entity, a universal constant whose properties we can measure and interpret. But there's a catch, one that strikes at the very heart of observational cosmology. Our entire perspective on the cosmos is framed by a single, unchangeable viewpoint, our location here on Earth embedded within the Milky Way galaxy. This brings us to the 19th mystery, the problem of cosmic variance. It forces us to ask a humbling question. Is the CUVB we measure truly representative of the entire universe, or is it merely a local sample, skewed by the particular patch of cosmic real estate we happen to inhabit? To understand cosmic variance, imagine you're trying to determine the average population density of the entire Earth, but you are only allowed to take a single census in one specific location. If you choose the center of a dense metropolis like Tokyo, your measurement will suggest the planet is overwhelmingly crowded. If instead you take your census in the middle of the Sahara Desert, you'll conclude that Earth is largely empty. Neither measurement is wrong, but both are incomplete because they sample only one specific environment. The true average lies somewhere in between, and to find it, you need to take measurements from many different, randomly selected locations. This is the essence of cosmic variance. It is the statistical uncertainty that arises from observing only a finite volume of the universe. The cosmos is not perfectly smooth. It is lumpy, with immense clusters of galaxies and vast, nearly empty voids. The CUVB we measure is the integrated light from everything along our particular line of sight out to the edge of the observable universe. but is our line of sight typical? The challenge is that we cannot, by definition, change our vantage point. We are stuck here. The volume of space from which we can gather high-quality data, especially for something as faint as the CUVB, is limited. It is a long, thin cone extending from Earth into the depths of space. This cone might, by sheer chance, pass through an unusually high number of galaxy clusters, or it might tunnel primarily through a cosmic void. If our cone is cluster-rich, the unresolved light from the myriad faint galaxies in those clusters could make our local measurement of the ultraviolet background appear brighter than the true cosmic average. Conversely, if our view is dominated by a void, the background would seem fainter. The problem is that we have no independent way of knowing if our particular cone is special or average. We are, in a sense, a single data point trying to determine the average of the entire population, with no way to assess the sampling error. This statistical uncertainty casts a shadow of doubt over some of the most fundamental conclusions we might draw from the ultraviolet background. For instance, the remarkable smoothness of the CUVB is a cornerstone of the cosmological principle, which assumes the universe is homogeneous on the largest scales. But what if that smoothness is just an illusion created by our limited perspective? It is possible, though unlikely, that our particular location in the cosmos is a uniquely placid and uniform region, and that if we could magically transport our telescope to another galaxy billions of light years away, we would see a much more varied and patchy ultraviolet sky. The cosmic variance problem means we can never be 100% certain that the properties we measure are universal truths rather than local quirks. Scientists combat this problem not with better telescopes, but with better statistics and sophisticated simulations. They use powerful computers to create virtual universes, vast simulations that obey the known laws of physics and generate realistic large-scale structures. Within these digital cosmos, they can place millions of virtual observers at random locations and have each one measure the simulated ultraviolet background from their unique viewpoint. By analyzing the distribution of these millions of measurements, they can quantify the expected range of cosmic variance. They can determine, for example, that if the universe is indeed homogeneous, then 95% of virtual observers would measure a CUVB intensity within a certain percentage of the true mean. If our real-world measurement falls well outside that expected range, it would be a tantalizing hint that something is wrong with our models, or that our place in the universe is genuinely unusual. Ultimately, the cosmic variance problem is a profound reminder of our own cosmic humility. It underscores that our knowledge of the universe is not absolute, but is always filtered through the lens of a single, privileged, yet limited observation point. It teaches us that in cosmology, every measurement must be accompanied by an estimate of its uncertainty, not just from instrumental noise, but from the fundamental statistical flukes of our position in space and time. As we push our observations to ever greater distances and fainter signals, the quest to overcome cosmic variance drives us to map larger and larger volumes of the cosmos, slowly building a picture that is less about our specific viewpoint and more about the universe as it truly is in all its averaged grand complexity. Now, let's turn our attention to some of the most violent and fleeting moments in the cosmos, where the serene dance of a star can be catastrophically interrupted by an unseen gravitational giant. This brings us to our 20th mystery, one that involves a spectacular stellar death and its potential to light up the darkness, the role of tidal disruption events. Picture a star much like our own Sun, following its graceful orbital path around the center of its galaxy. But if it wanders too close to the supermassive black hole lurking there, it encounters a force beyond comprehension. The black hole's gravitational pull is so immense that the side of the star nearest to it is tugged far more powerfully than the far side. This difference in force, the tidal pull, stretches the star horizontally while compressing it vertically, transforming it from a sphere into a thin, elongated strand of gas in a process poetically known as spaghettification. The star is literally torn apart as this stream of stellar debris rains down onto the black hole's accretion disk. It heats up to extraordinary temperatures, unleashing a brilliant flare of radiation that can, for a few brief months, outshine the entire host galaxy. And a significant portion of that furious flash is emitted as intense ultraviolet light. The question for cosmologists is whether these catastrophic events, happening again and again across the universe over billions of years, could leave a permanent mark on the cosmic ledger. Each tidal disruption event is transient, a cosmic firework that blazes brightly and then fades. But if they are common enough, the accumulated light from countless such flares, each contributing its brief, brilliant pulse of ultraviolet energy, could theoretically blend together into a steady, diffuse hum. It would be akin to standing in a vast forest where fireflies are constantly flashing. From a distance, you wouldn't see the individual flickers, you would perceive a continuous, gentle glow. Similarly, the combined ultraviolet output from all the TDs throughout cosmic history could be subtly woven into the fabric of the cosmic ultraviolet background. Assessing their true contribution, however, plunges us into a debate about frequency and detectability. The central unknown is just how often these stellar cataclysms occur. Current observations suggest that in a typical large galaxy, a tidal disruption event might happen only once every 10,000 to 100,000 years. If that rate holds true across the cosmos, then the number of these events happening at any given time would be relatively small, making their combined light too faint to account for a significant portion of the background glow. Their contribution would be a mere drop in the cosmic bucket, but what if we are missing a large population of these flares? It's possible that our current surveys are only catching the most powerful, nearby TDs, while a much larger number of fainter, more distant events go undetected. Furthermore, the rate could have been much higher in the past, during an era when galactic centers were more densely packed with stars, leading to more frequent close encounters with the central black hole. If that were the case, the early universe might have been illuminated by a near-constant strobe of these ultraviolet flares, whose faded echo could still be detectable today. The challenge of proving this hypothesis is immense, primarily because of the transient nature of the events themselves. To measure their total contribution, astronomers must conduct wide-field, time-domain surveys essentially, making movies of the sky to catch these flares as they happen. They then have to count them, measure their brightness, and extrapolate to determine the total number occurring across the entire observable universe. This is a Herculean task that requires years of dedicated observation. Each new survey that comes online with greater sensitivity and a wider field of view refines our estimate. Some recent studies have indeed suggested that the rate of TDs might be higher than previously thought, especially in certain types of galaxies, reopening the possibility that they could be a non-negligible source of diffuse light. Yet, even if their numbers are substantial, there is another hurdle. The light from a TD is not purely ultraviolet. The flare emits across the electromagnetic spectrum from X-rays to radio waves. The exact fraction of its energy that emerges in the ultraviolet depends on the details of the physics: the size of the star, the mass of the black hole, the angle from which we view it. This means that the UV fingerprint of a TD is not a fixed signature but a variable one. To accurately calculate their contribution to the background, we need a reliable average, which requires a large and statistically robust sample of events. We are still in the early stages of building that sample. The mystery of tidal disruption events therefore sits at the intersection of time-domain astronomy and cosmology. It challenges us to not only understand the physics of these violent occurrences, but also to piece together their collective history, to see if the ghostly sum of a billion stellar deaths might be shining faintly in the spaces between the galaxies. But now we must connect this vast extragalactic glow to a puzzle much closer to home, one that has troubled astronomers studying our own cosmic backyard for decades. This is the missing satellite problem, and it presents a fascinating paradox that the cosmic ultraviolet background might help to resolve. When cosmologists run supercomputer simulations of how galaxies like our Milky Way form within the framework of the leading dark matter model, a clear prediction emerges. The vast halo of dark matter surrounding a large galaxy should be teeming with thousands of smaller clumps of dark matter. Each of these clumps has the potential to attract gas and form a small, faint dwarf galaxy, a satellite orbiting the main galaxy. Yet, when we look around the Milky Way, we only see a few dozen such satellites. The simulations predict an army of hundreds. Observations reveal only a small platoon. Where are all the missing galaxies? This discrepancy is more than just a minor accounting error. It strikes at the heart of our understanding of dark matter and galaxy formation. One possible solution is that the vast majority of these dark matter clumps simply never manage to light up with stars. Perhaps the intense ultraviolet radiation from the early Milky Way or from nearby galaxies sterilized these small clumps, heating their gas and preventing it from cooling and collapsing to form stars. These would be dark galaxies, clumps of dark matter with little to no visible starlight. Another possibility is that our census is incomplete, that there is a vast population of ultra-faint dwarf galaxies orbiting the Milky Way that are so diffuse and dim they have simply escaped detection so far. Their starlight would be spread over a relatively large area, making their surface brightness so low that they blend seamlessly into the faint natural glow of the night sky. This is where the cosmic ultraviolet background offers a potential breakthrough. Imagine if these missing satellites, these thousands of predicted but unseen dwarf galaxies, are actually out there. They would be filled with hot, young stars just like any other galaxy, and those stars would produce copious amounts of ultraviolet light. Individually, each galaxy would be incredibly faint, far below the detection threshold of our current surveys. But collectively, their combined ultraviolet output could be substantial. If they are distributed throughout the dark matter halo of the Milky Way and other similar galaxies, their unresolved light would create a local fog of ultraviolet radiation. This fog would not be part of the truly extragalactic background. Instead, it would be a localized halo around our own galaxy and every other large galaxy. When we point our telescopes away from the galactic plane to measure the cosmic ultraviolet background, we are inadvertently looking through this faint local fog. The light from these missing satellites would therefore contaminate our measurement, adding an unexpected component to the diffuse glow that we would then mistakenly attribute to more distant extragalactic sources. This creates a compelling and elegant link between two major cosmological puzzles. The excess ultraviolet light that we can't quite account for in the background could, in fact, be the telltale signature of the missing satellites themselves. We haven't found them by directly imaging them because they are too faint, but we might be detecting their collective photon footprint. It's like knowing a large, unseen crowd is nearby because you can hear their combined murmur, even if you can't spot a single individual in the darkness. The missing satellite problem would then be partially solved. The satellites aren't entirely missing, they are just hiding, and their presence is revealed not by their starlight, but by the integrated ultraviolet glow they contribute to our sky. Testing this hypothesis, however, requires pushing observational astronomy to its absolute limits. Astronomers are using the most sensitive telescopes to conduct ever deeper searches of the Milky Way's halo, looking for the slightest overdensity of stars or a faint smudge of light that could be one of these ultra-faint dwarfs. Every new discovery of such a galaxy helps to constrain the models. Furthermore, scientists are creating detailed models of what the ultraviolet halo around a Milky Way-like galaxy would look like if it were filled with thousands of faint satellites. They then compare this predicted local glow to the actual measurements of the ultraviolet background, carefully subtracting the known foregrounds. If the models and observations align, it would provide powerful indirect evidence that the satellites are indeed there, shining too faintly for us to see directly but bright enough in aggregate to shape our view of the cosmos. This mystery beautifully illustrates how a problem in our local universe can be intimately connected to the largest scale observations, showing that the keys to understanding the cosmic ultraviolet background might be hiding much closer than we ever imagined. As we venture deeper into the realm of exotic possibilities, we encounter a concept so elegant it could simultaneously solve two of physics' greatest puzzles. This is the hypothesis of action-like particles, or ALP, and it proposes that the cosmic ultraviolet background might be the shimmering signature of a hidden dimension of reality. Actions were first theorized not to explain dark matter, but to resolve a profound imbalance in the strong nuclear force, the glue that holds atomic nuclei together. Physicists found that this force, for reasons no one could understand, appears to respect a certain symmetry perfectly, with no natural explanation. To fix this, they proposed the existence of a new, ultra-light particle, the action, that would restore this cosmic balance. Remarkably, this same particle, if it exists, has all the right properties to be the long-sought dark matter. But an even more fascinating twist is that certain variants, known as action-like particles, could be directly responsible for the diffuse glow we see in the ultraviolet. The mechanism behind this is a beautiful piece of quantum physics. In the presence of a magnetic field, action-like particles can undergo a miraculous transformation. They can oscillate or convert into photons of light. Imagine a hidden, invisible particle, one that permeates all of space, passing through the magnetic fields that are woven through the cosmic web of galaxies. With each encounter, a fraction of these particles could spontaneously transform into a faint whisper of ultraviolet radiation. This process would not be a violent explosion, but a steady, universal hum of conversion, happening continuously across billions of light years. The entire cosmos would be gently glowing with the light of these transforming particles. In this scenario, the cosmic ultraviolet background is not a fossil of stellar activity. It is a live broadcast of dark matter, very slowly revealing its true nature. What makes this idea so compelling is that it offers a direct test. The probability of an ALP converting into a photon depends on its mass and its coupling strength, essentially how readily it interacts with electromagnetic fields. Different masses and coupling strengths would produce a different intensity and spectrum of ultraviolet light. Therefore, the precise characteristics of the measured CUVB can be used to rule out vast swaths of potential ALP parameter space. Astronomers can take a proposed mass for an action-like particle and calculate exactly how much ultraviolet glow it should produce across the history of the universe. If the actual background is fainter than that prediction, that particular version of the ALP is ruled out. It's a process of elimination, using the cosmos itself as a gigantic particle physics laboratory. The persistent, unresolved signal of the ultraviolet background therefore acts as a strict boundary, telling theorists which of their beloved models are still plausible and which must be discarded. The hunt for this signature is a race between indirect detection and direct experimentation. While astrophysicists use telescopes to constrain ALP properties from the top down, particle physicists are building incredibly sensitive experiments on Earth, like the Action Dark Matter experiment, designed to detect the faint whispers of these particles directly. The cosmic ultraviolet background sits at the intersection of these two approaches. A confirmed detection in a lab experiment would immediately point astronomers toward a specific spectral signature to look for in the sky. Conversely, if astronomers could ever definitively attribute a portion of the background to ALP conversion, it would tell particle physicists exactly what kind of signal to search for in their detectors. This synergy transforms the CUVB from a simple astronomical curiosity into a crucial bridge between the immense scale of the cosmos and the infinitesimal world of quantum particles. The mystery of the ultraviolet glow is, in this light, a potential key to unlocking a unified theory that connects the very large with the very small, revealing a universe far more interconnected and wondrous than we ever imagined. But while we often picture galaxies as flat, spinning disks of stars, they are in fact encased within a vast and dynamic atmosphere, a halo of multimillion-degree gas that extends for hundreds of thousands of light years. This is the circumgalactic medium, or CGM, and it represents a critical yet elusive component of a galaxy's ecosystem. The connection to our mystery is direct. This hot, energized gas should glow, and a significant portion of that glow is predicted to be in the ultraviolet part of the spectrum. The combined light from the circumgalactic halos of every galaxy in the universe could be a major and previously overlooked contributor to the diffuse cosmic ultraviolet background. Understanding this isn't just about accounting for light. It's about reading the story of how galaxies breathe, how they live and die, written in the faint emission of their own extended atmospheres. To visualize the circumgalactic medium, imagine a galaxy not as an isolated island, but as the vibrant downtown of a sprawling metropolis. The stars are the bright buildings and city lights. The circumgalactic medium is the city's entire atmosphere, the air that fills its streets, the plumes of smoke and steam rising from power plants, the exhaust from countless cars, and the fresh air being drawn in from the surrounding countryside. This galactic atmosphere is not a serene place. It is a chaotic hub of activity, constantly being shaped by powerful forces from within the galaxy itself. Supernova. The titanic explosions of dying stars blast material outwards at tremendous speeds, injecting hot, metal-rich gas into the halo. The furious winds from starburst regions and active galactic nuclei act like cosmic hurricanes, driving colossal outflows that carry energy and matter far beyond the galactic disk. At the same time, the galaxy is also accreting fresh, pristine hydrogen gas from the intergalactic medium, which rains down upon the disk, fueling future generations of star formation. The circumgalactic medium is the interface where all these processes meet, a giant, simmering cauldron of inflowing and outflowing material. It is this very violence that lights it up. The gas in the CGM is heated to temperatures ranging from tens of thousands to millions of degrees through these energetic processes. When gas is heated, it radiates, and the specific wavelengths of light it emits depend on its temperature and composition. For the warmer phases of the circumgalactic medium, around 100,000 degrees, the primary coolant is the emission of ultraviolet photons, particularly from highly ionized atoms of oxygen, carbon, and silicon. As these ions capture free electrons, they release energy in the form of UV light. This means that every galaxy is surrounded by a giant, invisible ultraviolet neon sign, broadcasting the complex churn of its internal machinery. The problem is that this sign is incredibly faint. From our distant vantage point, the UV light from a single galaxy's halo is far too diffused to detect directly against the brilliant background of the galaxy's own stars. We are trying to see the warm glow of a city's air pollution from another continent. This is where the cosmic ultraviolet background becomes a powerful aggregate tool. While we cannot easily see the individual halo of a single, distant galaxy, the combined light from the halos of all galaxies across the entire observable universe should leave a statistical imprint on the diffuse glow. The background we measure should contain the summed-up whisper of every galactic fountain, every supernova shock front, and every stream of accreting gas that has ever existed. If we can accurately model the expected UV emission from a typical galaxy's circumgalactic medium, and then multiply that by the total number of galaxies, we can predict its contribution to the background. The challenge, of course, is that no two galaxies are exactly alike, and the properties of the CGM change over a galaxy's lifetime. A young, star-forming galaxy will have a much more energetic and brightly glowing halo than an old, quiescent one. Disentangling this specific signal from the other components of the background is a task of immense complexity, requiring detailed knowledge of galaxy evolution that we are still acquiring. The significance of detecting this signature would be profound. It would transform the cosmic ultraviolet background from a simple puzzle about the origin of light into a dynamic map of galactic feedback. The intensity and spectrum of the CGM's contribution would tell us about the total energy that galaxies are expelling into their surroundings. A stronger than expected signal would suggest that galactic winds are more powerful and widespread than our models predict, effectively verifying a key mechanism that regulates galaxy growth. Furthermore, by studying how this component of the background changes with redshift, that is, as we look back in time, we could trace the history of these energetic processes. We could observe when galactic winds were at their most violent during the peak epoch of star formation, and watch as they gradually subside in the quieter, modern universe. The faint, uniform UV glow would thus reveal itself as the cumulative record of galactic vitality, a chronicle of the powerful forces that shape galaxies from their halos inward, determining their size, their star-forming potential, and ultimately their fate. Having charted the vast contributions of galactic halos and circumgalactic gas, we now turn to a more surgical approach in our investigation, a method that moves beyond measuring the overall brightness of the cosmic ultraviolet background and instead listens to its subtle, hidden melodies. This is the domain of anisotropy and cross-correlation studies, a sophisticated branch of cosmic forensics that treats the sky not as a uniform sheet of light, but as a complex tapestry woven with faint patterns. The term anisotropy simply means a directional dependence, a variation from one point to another. While the CUVB appears remarkably smooth to a casual glance, it is not perfectly uniform. If we had instruments sensitive enough, we would detect incredibly slight fluctuations in its intensity, ripples in the cosmic pond that hold the key to identifying its sources. These anisotropies are the statistical ghosts of individual contributors, the collective fingerprint of all the structures, both seen and unseen, that generate the ultraviolet glow. The challenge lies in the fact that these fluctuations are minuscule, often buried deep within the noise of the instrument and the confounding foregrounds of our own galaxy. Detecting them is not a matter of taking a simple picture. It requires gathering immense amounts of data over the entire sky and then applying powerful statistical tools to tease out the faint signal. Scientists create all sky maps of the ultraviolet background with exquisite sensitivity. Then they analyze these maps to measure the autocorrelation function, a mathematical way of asking, if the background is a little brighter at this particular point, how much brighter is it likely to be at another point a specific distance away? The pattern that emerges from this analysis is like a cosmic barcode. Different types of sources imprint different patterns. The unresolved light from a uniform population of extremely distant, faint galaxies would create a very specific pattern of anisotropies characterized by a certain angular scale. The glow from nearby, warm gas in the circumgalactic medium of galaxies would create a different pattern altogether, one that correlates with the known positions of those galaxies. This is where the true power of the technique is unleashed through a process called cross-correlation. Imagine you are at a packed, noisy party trying to listen to a single conversation. Your brain performs a cross-correlation almost instantly. It focuses on the mouth movements of the person speaking and filters out the unrelated chatter. Astronomers do the same thing with the sky. They take their intricate map of the ultraviolet background's anisotropies and cross-reference it with other detailed maps of the cosmos. For instance, a three-dimensional map showing the positions of millions of galaxies created by massive redshift surveys. The question is simple. Do the tiny bright spots in the ultraviolet background line up with the locations where galaxies are densely clustered? If they do, it provides compelling evidence that those galaxies or structures directly associated with them are a significant source of the unresolved light. The results of these studies have been both confirming and startling. Strong correlations have indeed been found between the ultraviolet background fluctuations and the distribution of relatively nearby galaxies. This strongly supports the idea that the circumgalactic medium, the hot, gaseous halo surrounding galaxies, is a major contributor. The ultraviolet glow isn't just coming from between the galaxies, it's emanating from their extended atmospheres. However, more surprising has been the detection of a significant signal that correlates with the distribution of matter on the very largest scales, traces of the cosmic web itself. This suggests that a portion of the background originates from warm gas filaments stretching through the immense voids, the elusive warm-hot intergalactic medium, providing some of the strongest indirect evidence for its existence. Even more intriguing are the hints of an excess correlation on very large angular scales, a signal that seems to extend beyond what the known galaxy population can easily explain. This could be the signature of truly primordial sources, such as the decay of dark matter or the aggregated light from the first stars, whose distribution is so ancient and smoothed by the expansion of the universe that it imprints a signature on the entire sky. These advanced statistical techniques are transforming our understanding from a simple question of how much light to a complex inquiry of which structures are casting these specific shadows. Each unexpected correlation is a clue, a thread pulling us deeper into the cosmic web. By mapping how the ultraviolet background clumps and clusters in relation to the visible universe, we are effectively creating a chart of the invisible, highlighting the hidden connections between light and mass. This meticulous work demonstrates that the greatest mysteries are often solved not by looking for brilliant new signals, but by learning to read the faint statistical whispers that have been there all along, waiting for us to develop the mathematical language to understand their story. Yet, for all the intellectual ingenuity we've applied, from statistical cross-correlations to exotic particle physics, the ultimate resolution to these 25 mysteries likely rests not with better theories, but with better eyes. The final and perhaps most hopeful enigma is one of technological promise. The tools we have today, like the Hubble Space Telescope, have brought us to the edge of understanding, but they are fundamentally limited in their sensitivity and resolution when it comes to this specific, faint ultraviolet glow. The true breakthrough will come from a new generation of space observatories, missions currently on the drawing board that are being designed with the explicit goal of peering into this invisible universe and finally deciphering its secrets. Leading this charge are concepts like LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, and CETUS, the Cosmic Evolution Through Ultraviolet Spectroscopy mission. These are not merely incremental upgrades, they represent a quantum leap in capability, akin to the difference between Galileo's first telescope and the modern observatories of today. LUVOIR, for instance, is envisioned as a gargantuan telescope with a primary mirror up to 15 meters in diameter. To put that in perspective, Hubble's mirror is 2.4 meters across, and the James Webb Space Telescope's is 6.5. LUVOIR's colossal light-gathering power would be unprecedented, allowing it to see fainter objects than we have ever dreamed of observing. This is the key to solving the faint galaxies problem. Where Hubble and Webb see a haze of unresolved light, LUVOIR would see a sparkling field of countless individual dwarf galaxies and star clusters, finally allowing us to count them and measure their total ultraviolet output with definitive precision. It would weave a net so fine that nothing of significance could slip through. But these future missions offer more than just a deeper stare. They promise a clearer and more analytical vision. A central limitation of current data is the difficulty in obtaining high-quality spectra of extremely faint, diffuse sources. Spectra are the equivalent of a cosmic barcode, breaking down light into its constituent colors to reveal the composition, temperature, and motion of the emitting material. Cetus, as its name implies, is specifically designed to excel at this. It would carry advanced spectrographs capable of taking detailed ultraviolet spectra across vast swaths of the sky. This would allow astronomers to perform a chemical autopsy on the cosmic ultraviolet background itself. Instead of just measuring its overall brightness, we could analyze its spectral lines with exquisite detail. We could search for the specific ultraviolet fingerprint of highly ionized oxygen in the warm-hot intergalactic medium, providing undeniable proof of its existence and distribution. We could look for the unique spectral signature that would be left by the decay of certain dark matter particles, turning a vague hypothesis into a testable and perhaps even confirmable discovery. Furthermore, this spectral precision would finally allow us to untangle the complex web of foreground contamination. By measuring the exact spectral characteristics of the galactic foreground light with unprecedented accuracy, scientists could subtract it from the total signal with a level of confidence that is currently impossible. This would cleanse our view of the extragalactic sky, removing the ghost of instrumental artifacts and local dust scattering that has haunted previous measurements. What remains would be a pristine map of the true cosmic ultraviolet background, its anisotropies revealed in stunning clarity. The subtle patterns imprinted by the first stars, by galactic winds, and by the large-scale structure of the universe would stand out sharply, allowing us to attribute specific fluctuations to their correct sources with minimal ambiguity. The promise of these future missions, therefore, is not just to answer one or two of our 25 mysteries, but to fundamentally resolve the entire interconnected puzzle. They will move us from an era of inference and speculation into an age of direct measurement and confirmation. The question of the background's origin will be settled by a simple, direct census. The role of the circumgalactic medium will be mapped in brilliant detail around thousands of individual galaxies. The spectral shape anomaly will be diagnosed with the precision of a master surgeon. We will no longer have to guess about the properties of early cosmic dust or the frequency of tidal disruption events. We will have the data to state the answers with authority. These observatories represent the culmination of decades of cosmological questioning, the physical tools that will allow us to lift the final veil on the invisible universe. They promise to transform the cosmic ultraviolet background from a profound mystery into a definitive chapter in our story of the cosmos. A chapter that explains not only where the light comes from, but what it tells us about the birth, life, and ultimate fate of everything we see and everything we cannot. And so, as we reach the end of our journey through these 25 enigmas, a profound realization emerges. These are not isolated curiosities, but interconnected threads in a single grand cosmic tapestry. The faint glow of the cosmic ultraviolet background is far more than just empty space. It is a living, breathing record of the universe's entire history, from its first spark of starlight to the present day. Each mystery we've explored, from the missing Lyman-alpha blobs to the spectral whispers of dark matter, from the violent feedback of black holes to the gentle hum of the warm-hot intergalactic medium, represents a different chapter in this epic story. They are pieces of a puzzle that, when fitted together, reveal a cosmos of astonishing complexity and dynamic interaction, where the birth of stars is balanced by the death of galaxies, and where the visible world is shaped by forces we are only beginning to perceive. This diffuse light is a testament to the fact that the universe is a place of continuous transformation. It challenges the very notion of emptiness, showing us that the voids between galaxies are not true voids at all, but are filled with the echoes of creation and the subtle glow of ongoing processes. The journey to understand it has forced us to question our most fundamental assumptions, pushing the boundaries of physics and astronomy. It has revealed that our census of the cosmos is incomplete, that our models of galaxy formation are still evolving, and that the answers to the biggest questions often lie hidden in the faintest signals. The cosmic ultraviolet background is not a destination for our curiosity, but a gateway pointing toward deeper mysteries about dark matter, the first stars, and the ultimate fate of all we see. The story of this background is still being written. The next chapter will be authored by a new generation of telescopes and the brilliant minds that guide them. Missions like LUVOIR and CETUS, currently in development, promise to bring this invisible universe into sharp focus, transforming our statistical hints into definitive maps and our tantalizing hypotheses into confirmed discoveries. They will peer deeper into the infrared, unravel the secrets of cosmic dust, and finally count the legions of faint galaxies that have so far eluded our gaze. The progress in understanding this single phenomenon will undoubtedly ripple across all of cosmology, reshaping our comprehension of the cosmos on the largest scales. So, the next time you look up at a dark, starry night, remember that you're witnessing only the tiniest fraction of the reality that surrounds us. Beyond the familiar points of light lies a brilliant, invisible darkness, a cosmic background hum that holds the secrets of everything from the first dawn to the final fate of the universe. I encourage you to follow the progress of these discoveries as they unfold. The quest to decode the cosmic ultraviolet background is one of the great scientific adventures of our time, a reminder that the universe is far stranger, more wonderful, and more hidden than it appears. Keep looking up and keep wondering about the magnificent, invisible wonders that are waiting